Ever wonder how an AI goes from just following a set of instructions to actually learning? I mean, really learning on its own? Well, that's exactly the journey we're going to take today. We'll start with how they make educated guesses when things are fuzzy and go all the way to how they master some seriously complex strategies. Okay, so before we dive headfirst into all the complexity, check this out. Lesson is keep it simple. This actually comes from the winner of a university Pac-Man competition. Get this, they built this super sophisticated AI, and you know what won? A really simple set of rules. It's just a great little reminder that sometimes the most complicated answer isn't the best one. But for the really tough problems, yeah, we're gonna have to go a bit deeper. All right, so here's the game plan. First, we'll look at reasoning with uncertainty. Then, making the best possible decisions. From there, we'll jump into learning from experience, and even learning with no teacher at all. And finally, we'll tie it all together and see what this looks like out in the wild. Okay, first stop on our journey, reasoning with uncertainty. You know, the real world isn't neat and tidy, right? It's messy. You don't always have all the facts, and AI is in the same boat. So how in the world does it make a good, educated guess when it's flying blind? Well, the secret weapon here is something called a Bayesian network. The easiest way to think about it is like a map of what might cause what. It's all about probabilities. So it helps an AI understand that, hey, a burglary might set off an alarm, but so could an earthquake. The network's job is to help the AI figure out which is more likely. Let's actually build one using that classic alarm example. So we start with a node, just think of it as a bubble, for burglary. Then we make another one for earthquake. Now, since both of those things could set off a home alarm, we draw arrows from them to a new home alarm node. See? This simple little graph shows us exactly what could be causing what. Now, this is where it gets really cool. This is about updating beliefs on the fly. Let's say before anything happens, the AI thinks the chance of a burglary is pretty low, maybe 5%. But then, bam, the alarm starts blaring. The Bayesian network instantly crunches the new information, and suddenly the AI's belief that there's a burglary skyrockets to 51%. It hasn't seen anyone, mind you. It just reasoned its way there based on new evidence. That's what we call probabilistic inference, and it's a huge deal. All right, so our AI can think and update what it believes about the world. That's awesome. But just thinking about stuff doesn't really get you anywhere, does it? You have to do something. You have to act. And that brings us perfectly to our next section, making optimal decisions. And this really is the million-dollar question, isn't it? I mean, it's one thing to calculate that there's a 51% chance of a burglary. It's a completely different thing to decide what to do about it. Do you call the cops? Do you hide? How does an AI figure out the best sequence of moves to get the best result? The tool for this job is a framework called a Markov Decision Process, or MDP for short. Honestly, just picture a really complex game board. The AI is a player on this board. There are different squares it can be on. Those are the states. It can make different moves. Those are the actions. And for certain moves, it gets points. Those are the rewards. The catch? The outcome of a move isn't always guaranteed. The whole goal for the AI is to play this game in a way that gets it the absolute highest score in the long run. Let's make this real with something called the volcano crossing problem. So imagine you're the AI. You're on an island, and across a narrow path is a beautiful, scenic view. If you get there, you get a +20 reward. Now, in a perfect world where there is a 0% chance of slipping into the volcano, well, it's a no-brainer, right? You cross the path, you get your +20 reward. Easy peasy. But what if we crank up the danger? Let's say now there's a 20% chance he'll slip and fall into the volcano. That's a huge penalty, a -50. So what does the AI do? It does the math. It weighs the 80% chance of getting that sweet +20 reward against the terrifying 20% chance of getting a -50 penalty, and the answer it gets is +3.6. Now, that is way less exciting than +20 for sure, but it's still a positive number. So believe it or not, the most rational, optimal action is still to try and cross. The AI has officially made a calculated risk. Okay, but think about this. In all our examples so far, the AI knew the rules of the game. It knew the probability of slipping. It knew the reward for the view. But what if it doesn't? What if you just drop an AI into a brand new world with no instruction manual, no guide at all? Well, now we're talking about learning from experience. And this is where something called reinforcement learning comes in. It's a complete game changer. With reinforcement learning, or RL, the AI isn't handed the rulebook. It has to write the rulebook itself, just by trying things out. It's exactly like when you play a new video game for the first time. You don't know what the buttons do, right? So you just press them. You see what happens. You get points, you lose a life, whatever. You get feedback, and slowly, through pure trial and error, you start to figure out how the world works. That, in a nutshell, is reinforcement learning. All right, let's take this one step further into some really mind-bending territory. What if there are no rewards? No points for getting it right, no penalties for getting it wrong, no teacher, no hints, nothing. Just a giant, messy pile of data. The goal? Find the hidden patterns inside. This is called unsupervised learning, and to see how it works, we're going to try and crack a code that stumped humans for centuries. Say hello to the Capiales cipher. This is a real thing, a 105-page manuscript from the 1730s, just filled with these bizarre symbols and some Roman letters mixed in. For more than 250 years, the smartest people looked at this and had no clue what it said. It's the ultimate test for an AI, right? Can you find a hidden structure in what looks like complete chaos? So, to tackle this, researchers turned to an algorithm called expectation maximization, or EM. Just think of it as a two-step process that repeats over and over. Step 1. The E step is expectation. The AI makes a totally random guess. It might say, you know what, I'm going to guess that this funky-looking symbol is the letter A. Step 2 is the M step, maximization. The AI then says, okay, if that symbol is an A, let's update my entire understanding of the code based on that guess. And then it just does it again, and again, and again. It's a loop of guess and then refine your guess, thousands, millions of times. And after doing this over and over and over, something incredible happens. The chaos, the gibberish, it starts to morph into actual words. What you're seeing here is a real piece of the deciphered text. An AI working completely on its own cracked a 250-year-old code and revealed the inner workings of a secret society from the 1700s. It literally learned a lost language without a single teacher. So, we've gone from an AI figuring out if a home alarm is serious, all the way to cracking an ancient cipher. These ideas are obviously super powerful, but it's easy for this to feel a bit abstract, right? So how does this stuff actually show up in our world today? Let's bring it all back home. This stuff is actually everywhere, once you know where to look. Those Bayesian networks we talked about, they're working behind the scenes in your email's spam filter and in really advanced medical diagnosis software. Markov decision processes, the MDPs, they're the brains behind a lot of modern robotics and complex supply chain logistics. And reinforcement learning, that's the magic that powers those incredible game-playing AIs, and it's also what's behind the recommendation engine that suggests what you should watch next. But look, it's not a perfect science, not even close. AI has some massive challenges to overcome. There's this hilarious and also terrifying thing called reward hacking, where an AI cleaning robot figures out the best way to get its job done reward is to just hide in a closet where there's no dirt. Seriously. Then you've got adversarial examples, where someone can design a funky pair of glasses that tricks a facial recognition AI into thinking they're a completely different person. And beyond that, you have the really serious issues like fairness and bias, when an AI learns bad habits from biased data, and the whole black box problem. That's when these systems get so complex, we literally don't know why they made the decision they did. So that's the journey. It's pretty amazing, right? We've gone from simple, rule-based reasoning to machines that can actually learn and discover patterns that humans might miss entirely. It feels like we've crossed a threshold. The big question for all of us is no longer, can machines learn? They can. The question now is, are we teaching them the right lessons?